let's move on from where we were the other day, which was starting to talk about Faraday's law, and then we'll get into Lenz's law and do the pictorial method, which the three-sentence quiz was about. Okay, so we'll do that. What we saw the other day was when we had the North Pole aimed at the magnet and aimed at the coil, sorry, and we brought the magnet closer to the coil, the needle on our current meter moved to the left. When we took it away again, it moved to the right. When we just let it sit in there, it didn't do anything. Even though there was lots of flux, the key is you've got to change the flux to induce a voltage that causes the current. Okay? And so now what's our prediction here? If the North Pole is aimed at the coil and we move the North Pole in, the needle deflects left. If we turn it around, go this way. So if I do the South Pole, someone make a prediction. Garija said. To the left. No, to the right. She said to the right. We all heard that. To the right. And she was correct. So it does go to the right. Okay, and of course if the magnet is then moved away from the coil, it's going to go to the left, which it does. Okay, then we're going to use the other end of the coil. Now I'm going to go to the other end of the coil. I'm going to use the North Pole, and I'm going to bring it toward. Okay, prediction. Who votes for right? Yeah. Who votes for left? Lots of votes for left. Okay. Why do you say right? You're the only one who said right. Intuition, okay. Let's see. North Pole coming in. What does it do? It moves to the right. Yeah, it was the only one correct. Okay. Now, that shouldn't be too surprising because when we brought it in from this side, it went left. If we switch sides and turn the magnet around, it should go the other direction. Right? So I think we're okay with that. At least me and Yev are. Anybody else? What's this last one? Magnets rotate it back and forth near the end of the coil. Well, it depends how I rotate it. Let me try this. So what I'm going to do is actually, like I could rotate it like this. What if I rotate it like that near the end of the coil? That's not going to be very effective. Nothing's going to happen there. I'm really not changing the flux. If I rotate it like this, what's going to happen? Are you going to see something over here? It's going to go like this? Yeah? Okay, let's see. I don't know if this is going to work at all. We'll try it out anyway, right? Here we go, right? Whoop, doop, doop. What do you think? Go back and forth? Yeah, it wiggles back and forth. So as I rotate the magnet, this thing wiggles back and forth. Okay? And again, this is really why, for instance, lights are on in this room. Because somewhere, probably a long way from here, someone's got some trained squirrels that are moving magnets in and out of coils or something like that. Or they've got a hydroelectric generating plant and the water is rushing down and causing some turbines to spin, which is really actually got a fixed coil and you're moving magnets around that coil. Okay? And that's generating electricity we're using right here. Okay. Okay. Are we okay with that? And so we saw all this stuff happen. We saw needles going left and right or not moving at all. And we're going to summarize all those. At least we're actually going to let Faraday summarize all this. So Faraday, who again was born about 200 years ago, did lots of experiments on this. He was an incredible experimenter, really well known for his experimental technique. Okay? And he was the first guy who really quantified this. And basically, he summarized everything we've just seen in this nice little compact package. The induced voltage, that's that squiggly E, is minus N. N is the number of turns in your coil, times the time rate of change of the magnetic flux. Okay, so that phi, capital Phi there, the Greek letter is magnetic flux, so you have to have a change in magnetic flux with respect to time. You can have all the flux you want, and if you don't change it, you get nothing. If you change the flux, you get something, and if you have a really fast change in flux, then you get lots of voltage. Okay, and there's a whole other law about this minus sign, which we will get to. That's Lenz's law. Okay? Questions on this at all so far? Okay, and again, this is the basis of most electricity generation, and it's also involved in, distributing the electricity from here, from where it's, sorry, not here, to here, from wherever it's generated, which can be hundreds of miles away. Like northern Quebec has all sorts of hydroelectric power plants, and they supply tons of electricity to New York City. That's a long way. Okay? And to send that power without losing most of it along the way, you do all sorts of things which rely, again, on Faraday's law. Okay, so we didn't have any batteries going on here, but we still got a current, and so a changing flux in a complete circuit can actually act like a battery. You can get a current. Okay, questions on any of that? Okay. Then we get to Lenz's law, which you guys investigated a little bit on the pre-session. This is Faraday's law. Actually, exposing a coil or loop to a changing magnetic flux will generate a current if the circuit is complete, because that voltage you get out of Faraday's law. And then the direction, it's the direction that's Lenz's law is all about. And that's really about this minus sign that's in Faraday's law. And it's kind of a cool thing. Okay, so this changing flux, and this is what we did to this coil, right? By me moving the magnet closer or farther, I was changing the magnetic flux through that loop. And the change in magnetic flux induces an EMF, a voltage, and if you have a complete circuit, then you get a current. Well, what does a current do? Current produces a magnetic field, and that magnetic field tends to oppose whatever produced the change in the first place. Okay? So the basic idea is this. So I've got this coil here. When I move my magnet in toward the coil, there's actually a resistance. I don't feel it, but it's there. Okay? This thing resists it. It actually acts like a magnet that points the other direction. There's a current running around the coil such that this coil acts like a magnet with the north pole facing out. So then I bring my north pole closer to it, and then there's a repulsive effect there. So it opposes whatever's producing the changing flux, which is the motion of this magnet. Conversely, if I take the magnet from here and I move it away, okay, this actually, the current runs the other way, which makes this end act like a south pole, and it's trying to prevent this from moving away. Whatever it's preventing motion, trying to prevent motion in all cases, because the motion of the magnet is what's producing the change in flux. Okay, so it's kind of a neat effect. And always acts to oppose whatever produced the change. Okay, and so basically, these things, coils, loops, they don't like change. Many of us don't like change either, but that's okay. And they try to counteract any changes in flux, magnetic flux, that we impose on them. Now we will win, okay? We can actually cause the change, but while we're producing the change, it fights us, okay? And so this tendency to oppose is where that minus sign comes from. Are we okay with that? Any questions so far? Okay. So this is like really how electricity is generated. Okay. I got a bunch of magnets here, just these regular old horseshoe magnets. There's a coil inside there, which is currently not turning, and this is pretty old, so it doesn't turn very well anymore. But if I really crank on this thing, I can get the loop to move through the magnetic field. And there's a light bulb here. What do you think the light bulb's going to do when I turn the crank? It's going to what? It's going to light up. That's the idea. Whether it really will, we're not sure. So I got to put it down to make it happen, because it's really hard to turn. Okay, and the front row can tell that it lit up. At least this half of the front row can tell. Okay, and it doesn't like to be turned. It squeaks a lot, and complains a lot, but it still produces a charge. Okay, there's actually a little switch on here. I can disconnect the light bulb from the magnet. Okay, do you think it's going to be easier, harder, or just the same for me to turn this? It's going to be what?
I don't know.
No difference at all. because there's all sorts of friction in here. It's probably just about the same, but pretty close. But it actually is harder to turn when it's connected to this load. Okay? Yeah, somewhat harder. It's with a better system, it'd be easier to see. I'll bring a better one in a couple of days, and we'll really do it then. Okay, so there's that. Then there's this other neat demo. That says drop a magnet through a copper tube. Okay, so I'll do that. So here's a copper tube, and here's a little disc magnet. You could stick this on your fridge. Okay? And so it's going to be dropped through this height here. Okay, so let's just get a feel for how long it takes to drop a magnet from rest through that height. Okay, ready? 1, 2, 3, go. Okay, not very long. All right. So I'm going to try the exact same experiment, but I will just drop it through the copper tube. It's not a real snug fit. There's space between the walls of the tube, the inside of the tube, and the magnet. Okay, so it really doesn't touch the side of the tube, at least very much on the way through. Okay, we ready? Okay, here we go. 1, 2, 3, go. Okay, where'd it go? It's coming out? I don't know. There it is. Okay, takes a long time. Okay, so what was responsible for the magnet basically dropping as if it had a parachute attached to it? That's what it acts like. And it's fun to just watch this as it falls down. You know, I could drop this a bunch of times and just spend the whole rest of the class just watching this. But to prevent myself from doing that, I will pass it around so you can try it yourself. Okay, so try that. Watch it as it falls down. Okay, so this is Faraday's law, Lenz's law. And so there is Lenz's law again. We saw that already. So what happens here is we're exposing different parts of the tube to a changing magnetic flux because the magnet is falling down through the tube. Okay? Does that sound okay so far? So the flux is changing because the magnet is moving through the tube. Flux is changing in various parts of the tube. Okay? And so if this was a plastic tube, we wouldn't get any effect. It's very important that it's a conducting tube. And copper is a very good conductor. Because then what happens is you can, so even the plastic tube will have a change in flux, it just can't do anything about it. The conducting tube, you can set up currents that swirl around the tube. And those currents produce magnetic fields. And those magnetic fields oppose whatever produced the change in magnetic flux in the first place, which is the motion of the magnet. So they act to slow down the magnet. They can't bring it to a stop. Okay? If they brought it to a stop, you wouldn't have any change in flux anymore. Okay? So they can't completely take the motion away, but they can really slow it down. That's a pretty dramatic difference between dropping it through the air and dropping it through the tube. Okay? Okay, any questions on that at all? Okay, we'll do one last one, and this is where I'm going to get Yev to help me. So we have 2 tracks. Okay, these are just angle brackets, aluminum angle brackets here. So I'm going to get Yev to hold one, and I'm going to hold the other one at approximately the same height. Okay, and then we get 2 balls. Are they identical?
Yes.
Yes, he says Yev. Okay, so on the count of 3, we're going to let the balls go, and we're going to see which one gets to the end first. Okay, ready? 1, 2, 3, go. So raise it up a little bit. Let's get it down here. Okay, so it, for some reason, doesn't really like going down. Mine was fine, you noticed. But yours still isn't there. Finally, it's there. Thank you. Okay, so what do you think? My track was better than yours?
Yes.
Yes? Okay, so if I do it on this track, it's going to work just as well as when my ball went down this track. Is that right? Let's see. No. So it's not the track. Tracks really are identical. It's something to do with the balls. And they look identical, but they're not. And I don't know where the other one, there's the other one. Thanks for pointing that out. So they look identical. They certainly stick to each other, but in fact, one of them is a magnet and the other one is not. And ooh, this is on. Let me turn that off. So this is the one that I had before. Doesn't stick to this piece of steel. This is the one that Yev started with. It sticks. So it's magnetic. Okay, sorry about that. I gave you the magnetic one. Okay, so the other one's non-magnetic, goes down that conducting pipe, no problem at all. The magnetic one, the problem there is you're exposing this aluminum to a changing flux because of the motion of the magnet. And so there are currents set up inside this solid parts of this track that act to oppose whatever's causing the change in flux, which is the motion of this magnetic pole. So it acts to oppose that motion. And so it slows the motion down. Okay, really shouldn't be able to bring it to zero. We actually could stop it, but that's actually, there was some friction there and stuff. So, so are we okay with that? So again, pretty dramatic demonstration, the difference between just a regular old metal ball rolling down there and a magnetic ball rolling down there. Okay, get that change in flux can really produce some interesting effects. Okay, questions on that? Okay, we got one last demo to do, but we'll save that for later. This is this guy. Okay, so I think we're going to talk about the pre-session. No, we're not. We're going to talk about the pictorial approach to Lenz's law, and then we'll do the pre-session. And I know I'm covering the same ground that was covered in the movie and stuff, but that's okay. So we're going to draw these three pictures. This is how we're going to do Lenz's law. And the Lenz's law question is, which way is the induced current in the loop when this happens? Okay? And so this is how I suggest you do it. Draw this set of three pictures. And part of the process is knowing how to use your right hand to figure out which way the field is when your current goes this way or that way. Okay? Okay, so we'll do this. So in general, we'll have loops that are in the plane of our page. And so if you run your current around the loop in this direction, then you use that right-hand rule where your fingers are curling and your thumb's in a straight line. And last class, I used my thumb to be the current because I had currents in long straight wires. You can always use your thumb as the current if you want. Okay, so I can put my right hand like this on that wire, and I've got my fingers going into the screen above the wire inside the loop. Okay? If I did it this way, my fingers would be coming out of the screen, but that's below the loop. So outside the loop, the field lines come out of the screen, they wrap around, they go back inside the loop. Okay? So you can certainly follow, I really want to do it this way. Follow the current around with your right hand, and inside the loop, your fingers will always go in when the current is going that way around, which is clockwise, isn't it? And of course, the opposite direction. Okay, so if you have the current in the loop, this is the field produced by that current inside the loop. Same with that. If you have the current going the other way, the field produced by that current is out of the page. Are we okay with that? So your thumb can always be the current if you want it to be. However, you can actually reverse this rule and just say, whatever curls, whatever goes in a circle, that's my fingers, and the other thing is the straight line. So in this case, for instance, I could say, my fingers are curling the way the current goes around the loop, and my finger points, that's not a finger, that's a thumb. My thumb points out of the screen, which is the way the field goes produced by that current inside the loop. Okay? So you can reverse it if you want. You can always have thumb be the current if you want. Your choice. Any questions on applying the right-hand rule there? But all we're trying to do is answer the question, what direction is the field produced by a current that goes this way?
When your thumb is the current, how do you know that like B is going counterclockwise?
So what we do know here, what we know first is which way the current goes, and then we're using our right hand to figure out which way the magnetic field goes. Okay, so I could hold my hand like this at this point, and I've got my thumb being the current, and below that, my fingers are coming out of the screen. Of course, above that, they go into the screen, okay? Which is true. These field lines got to go somewhere. They actually wrap around like this. They're actually little circles around the wire here. But I don't care what's going on outside at this point. I only care about what's going on inside. Okay? Okay. Okay, so just to go over the pictorial approach, here's the same example I gave in the movie. Okay, so we got a wire loop. We've got a magnetic field. We changed the field. We actually increased the magnitude of the field by a factor of 2. And while the field is changing, which way is the induced current? And you only get an induced current while the field is changing. Okay? And so we've got this pictorial method, and you draw some pictures. And one picture you draw is what I call a before picture. So at the beginning, what does the scenario look like? And then you draw the after picture. After you're done making some change, what does the situation look like? And you're just drawing the loop and the field lines through it. That's all that shows up on your pictures. And then you draw what I call a to oppose picture. So you look at the before and after picture and you say, has there been a change? If there hasn't been any change, you can stop there. You say, okay, there is no induced current because there's nothing to oppose, no change to oppose. But if the before and after pictures are different, then there's a change in flux to oppose. Okay, so you draw the to oppose picture, and the to oppose picture is a two-step process here. First, you show the direction of the field that the loop has to produce to oppose the change between before and after. And then you get your right hand going, and you say, well, if that's the field direction, my right hand tells me which way the current must be going around the loop to create that field. Okay? So the fields in the before and after picture come from something external to the loop, and the only field that's produced by the loop itself is in the to oppose picture. Okay? Okay, so let me go through that pictorially. So in our scenario where we start with some field into the page, this is my before picture. Nothing magical about 3 lines here. I've shown 3 x's going through the loop. You want to draw 5 or 2 or 17, doesn't matter. Okay? Draw a bunch, whatever you want. But then we doubled the field. So I'm going to draw, if I drew 3 in my first picture, I'm going to draw 6 in the next picture. If you drew 17 in the first picture, you're going to draw 34 in the next picture, etc. Okay? But the critical thing is we got more x's, more field lines passing through the loop into the page after we make the change than we started with. Okay? All our pictures are going to show that. Are we okay so far? And again, this could be, here's a loop. What's producing this field? Maybe it's this magnet. Okay? I'm holding my magnet right here, and I'm getting this to happen. What could I do with my magnet to get that to happen? More field lines going through it. If I just get closer, and now I'm holding the magnet not here, but here. Okay, now I got more field lines going through into the page than I had before. Okay, so to oppose the change, what is the change? We've added field lines into the page. Would everybody agree that's the change between before and after? We've added field lines into the page. So if the loop opposes that change, the loop sets up its own field in what direction? Into the page or out of the page? Out. Okay? If we add field lines in, it says, I'm going to add field lines out. How many field lines do you want to draw in your to oppose picture? You know, 1 is fine. 1 is great. This is a very qualitative way just to get current direction. That's all we're using this for. Which way is the current going? Okay? So step 3 is, and I've got step 3 and 4, but step 3 is actually just show the field coming out of the page. This is the only field in this set of 3 pictures created by the loop itself. Okay? These other 2 were created by something external to the field, such as me holding the magnet at various distances away. This one's created by the loop itself to oppose the change between before and after. Well, how does it create this field? It runs current around itself in a particular direction. It can either go clockwise or it can go counterclockwise. And our right hand tells us, if I want my magnetic field, that's going to be my thumb, to point out of the screen, then I got to run current, that's my curling fingers on my right hand, I got to run my current counterclockwise to produce that. So that's the direction of the induced current produced by the loop while we're making this change, adding field lines into the page. So then we came to this. This is in the pre-session quiz. So we had these 6 possible before pictures, a single after picture. We knew exactly what was going on afterwards. Some field going through the loop. It's a square loop in this case. Some field going through the loop into the page. And then 2 possible 2 opposed pictures. So the first question was, in pictures P and Q, which way are the currents? What are the current directions that will produce these fields? Okay? So that's just a right-hand rule question. So in picture P, to answer that question, I'm going to point my thumb into the screen. That's the way the magnetic field goes. And to produce that magnetic field, I must have current running clockwise, that's what my hand says, around the loop. Okay? And I'm doing field is thumb and current is my fingers. You don't have to do it that way. You can have, that arrow can be your thumb. Okay? That can be your current. And your fingers go into the screen above that wire that's carrying current to the left. And that's correct. That's consistent with the picture there. That's the way the field goes. So you can, thumb can be field or current, your choice. Are we okay with that? Okay, so then I would say P, we must have current going clockwise to produce that field. And so in Q, it's got to go the other way if we want to produce the field the other way. And your right hand will tell you that too. Okay? And you could do your right, I would do my right hand this way. My thumb is my field coming out of the screen, and my fingers are going counterclockwise, which is what that, if you follow the current all the way around, it's what it's doing. Are we okay with that? Okay. Okay, so then we got a bunch of possible before pictures, 1 after picture, and 2 possible 2 opposed pictures. And then I think we said we want what to happen? We want to produce P, right? Is that what we wanted? It was Q. Okay. Well, let's figure out. We'll do it all. Okay? Let's just go start with 1 as before, start with 1 as a before, end with that after picture. What's the 2 opposed picture for that? If you start with 1 as your before picture, end with afterwards. What's the change there? You've gone from a bunch of field lines in to fewer field lines in. So what does the loop do? The loop says, you've taken away from me field lines in. So to oppose that, I'm going to produce a field which is in. And that is P. Yeah, I guess it was Q, wasn't it, that we asked about, because P is not the answer to the pre-session quiz. 1's not the answer to the pre-session quiz. But if you went from 1 to after, then P would be the 2 opposed picture. Are we okay with that? And I'm going to quote from one of you guys. Okay, so picture 1, they said, you're adding field lines out of the page. Maybe. Okay, I looked at it as taking field lines away into the page, but adding field lines out of the page, that's totally the same thing, okay, as taking things away that are in. That accounts for the decreased number of field lines into the page, fine. Therefore, the opposed picture should be directed into the page. That was P. Great, great answer. Okay, what do we start with 2? Let's start with 2 and go to after. What does the loop do? Loop says, that's fine with me. You're not changing anything. I'm good. I'm not going to run any current around myself at all because you're not changing the flux. So, and exactly right. No change occurs, no induced current. So neither one of those, P nor Q, go with 2 to after. 2 to after, you get nothing. No change. Are we okay? Okay. How about 3 to after? What have we done there? We start with 3, some field in, to after, more field in. Have we made a change? Sure. The loop does something to oppose that change. What does it do? It says, you've added field lines into the page. So I'm going to put a field which is out, and that's picture Q. Okay? And it turns out that, in fact, 3, 4, 5, and 6 are all consistent with that. Okay? So to go from 3 to after, what have we done? We've added field lines into the page. 4 to after, we've added field lines into the page. 5 to after, we've added field lines into the page. That canceled out this single field line out of the page and then added 4 more in. 6 to after, we've added a bunch of field lines into the page. Okay? So the loop, in all those cases, 3 to after, 4 to after, 5 to after, 6 to after, says to oppose the change that you did, I'm going to produce a field out of the page. Okay? Now, if the time intervals were the same in all 3 cases, those were 4 cases, in all 4 cases, we'd get a different amount of current in picture Q. Okay? So the size of the current would be different because we'd be changing, the change in flux would be a different amount in that time interval. But all we're caring about here is what direction is the induced current. Okay? So the magnitude is a different question. But you can say 6 to after is going to give you the biggest magnitude induced current if all those changes occur in the same amount of time, because that's the biggest change in flux. From 4 field lines out to 4 field lines in is a lot bigger than anything else we did up there. Are we okay with that? Okay. Okay, so let's turn it over to you for a while. So on your worksheet, on the other side, in fact, the top one I'm going to leave to you, okay? But this is Lenz's law example 1, which is the second thing there. And it does say example 1 in the second thing. So, and the sheet says exactly what this says. A wire loop is located near a long straight current carrying wire. Apparently the current is constant, as I marked on the diagram. It's directed to the right, obviously. And what we're going to do is we're going to take our loop and we're going to move it. It starts here, and we're just going to move it this way. Okay? And so while we are moving the loop, in what direction is the induced current? And I'm going to suggest that to answer the question, you draw a before picture, an after picture, and a to oppose picture, and just follow the whole pictorial method. Okay? So give that a shot. Which way is the induced current in the loop? Is there an induced current in the loop? If there is, which way does it go? Okay, so first of all, when we're drawing our before picture, we need a source of magnetic field. Okay, do we have a source of magnetic field here? In this scenario, do we have anything that's producing a field? There's a wire. And what's going on in the wire? Is there a current in the wire? There is. Okay, so currents can produce fields. So this thing is producing the field. So you got to figure out which way the field goes. Okay, so there's one application of a right-hand rule. And this loop is going to stay above the wire. And so above the wire, according to your right hand, the field produced by the wire is directed this way or this way. Michelle says toward the back of the room, out of the screen. Okay, and you get that with your right hand? There it is. Okay, so you can hold your hand like this. Your thumb can be your current. Above the wire, your fingers are pointing out of the screen. Okay. If you did it below the wire, they'd point in. But we don't care about what's going on below the wire because our loop never gets there. Above the wire, this has field. This is experiencing a field out of the screen. Are we okay with that? Okay. So we move it to somewhere else. Okay. Is there any change between the before and after picture? There is? Because the further away you get from the wire, what happens to the field? The smaller it gets. Exactly right. Okay. Okay, so we got 52% counterclockwise, 41% clockwise, so we're not too different from 50-50 so far. But this is what I got for my before and after pictures. Okay? So I've got field coming out of the screen when the loop is close. I got a bunch of field lines. I've got fewer field lines. Don't worry about whether it's 4 to 2 or 6 to 1 or whatever. It doesn't really matter. What matters is more here than there. That's the key. Are we okay with that, the before and after? And again, this field is produced by the long straight wire. Okay, There's a change between before and after. We've made a change in flux. So the loop says, I don't want to see any change. I'm going to try and bring the after picture back to the before picture, in a sense. Okay, so what does it do? And it's never going to get it all the way back, but it tries. So I've got an out of the screen field line on my two opposed picture. Are we okay with that? Okay. So what have we done? We've subtracted field lines out of the page to go from there to there. So the loop says, well, I'm going to add one back. And then you get your right hand going and say, well, if your field runs out of the screen, your fingers wrap around counterclockwise. Okay. Questions on that? Okay, but we weren't very different from 50-50 on that one, were we? 52, 41. Few people even voted for no current at all. Okay, so let's see if we can improve this as we go forward. Let's do another one. Okay, so now we're going to do it's a very similar scenario. This is a constant current, and the loop is here. It's going to be in the same starting position as it was before, and we're going to move it this direction. We're going to slide it along this way. Okay? So as we slide it along to the right or to the left, doesn't really matter. In what direction is the induced current? Okay, I'm seeing a lot of great sets of pictures here, before and after. So let's see what we got here. Let's see if we can do better than 52% on this one. 79% have gone for answer 3. And so let's see if our before, after, and two opposed pictures are consistent with us. And so we'll have a look and we'll say, okay, our before picture is that. And our after picture, well, we've slid the loop a little to the right, but it's the same distance away from the wire. So it's feeling the same field strength over there as it did at the beginning. So that sounds good. What's the loop do? Does it see any change to opposed here? So the loop is perfectly happy. You haven't imposed a change on the loop. It's fine with you. It doesn't do anything to oppose. There's no change to oppose there. So that's great. Questions on that? Okay. Let's try a third one. Okay. So just so you understand the picture, what it is just this loop is lying flat on the screen and the wire is in the plane of the screen going this way. Okay, so everything is in the plane of the screen basically. And it's just like this is lying on top of the screen like so. Okay, just like this. That's a smaller scale version of it. It is not this way with the wire going straight through the middle like that. It's not like that. It's just this is lying flat on the screen. The wire is in the plane of the screen. And we're not going to move the loop. So if we didn't move the loop and the current was constant, then nothing would be changing. So what we're going to do is we're going to keep the loop where it is, but we're going to increase the current. And you can go back and think about what if we left the loop here and increased the current? Would that be any different than this, et cetera, et cetera? So think about those kind of scenarios. But here's a scenario where the loop is right on top of the wire, and we're increasing the current in the wire, and the current is moving to the right. Okay, so see what you think of that. Okay, so we're actually back to 52% again, which is what we started with in problem 1. But this is actually much harder scenario to consider. Okay, so let's see what we got here. So we'll draw before and after in two opposed pictures, okay? And I'm going to draw mine like this. So above the loop, field comes out. Below the loop, field goes in. So I've got a bunch of field lines going into the screen below, in the lower half of the loop. A bunch, well, two, coming out. Net magnetic flux in that picture is what? It's actually 0. That's right. Net magnetic flux is 0. Because you got an equal number of field lines coming out as they're going in. Okay, so then you increase the current, and then you get more field lines coming out in the top half and more field lines going in the bottom half. And what's the net magnetic flux in that picture? Also 0. Okay, and that's really the whole key. Have you changed the total amount of flux through the loop? And it turns out you have not. In fact, your before and after pictures, they look a little bit different, but the net change in magnetic flux is actually 0. So that's a tricky one. If you put this loop anywhere else, try it out. Put the loop anywhere else, and you'll get some induced current. Okay, let me do this last demo because it's kind of cool, and we'll explain it next time. So, I have a coil. It's plugged into the wall. I have an aluminum ring. I'm going to stick it on here, and I'm going to turn on the switch, which turns on the current to the coil. There's a piece of iron that runs right through the coil and sticks out of the coil, and this is what the aluminum is stuck on. Okay? When I turn on this, what do you think is going to happen? Any predictions? Anything going to happen? It's going to do what? There we go. 1, 2, 3, go. Whoop. Okay, and then if I can just rest it there, and it'll just stay. It's levitating on there. Okay, and so we'll come back. We'll start with this again next time because it's kind of a cool demo. Whoop.